Here we have an example. A rocket is fired from Earth towards the Moon. For letter A, find the minimum speed needed to shoot a rocket straight up to a height above the Earth's surface equal to the Earth's radius. For letter B, find the minimum speed that would allow the rocket to escape from the Earth completely. This is also called escape velocity. Neglect air resistance, the Earth's rotation, and gravitational pull of the Moon. For letter A, we find the minimum speed needed to shoot a rocket straight up. We look at the energies at the surface and at an elevation. At the surface the energies is shown here in equation 79. Here the rocket has both kinetic and potential energy since it is launched with an initial speed or minimal which we need to find out. So we have the expression shown in equation 80. Now, at the elevated position where the rocket perhaps runs out of fuel and stops moving, the energies are shown in equation 81. Here we see it has only the gravitational potential energy and we have equation 82. Since the distance is just equal to the Earth's radius, then the distance r where it is measured from the Earth's center is equal to twice of the Earth's radius and we have the energy shown in equation 83. Equating the equations for the energies we have equation 84. Substituting the equations we obtained earlier we have equation 85. Further manipulating the equation we arrive to a simplified version shown in equation 86 where it is a function that will allow us to solve for the minimum velocity needed to launch the rocket. We then substitute the known values as shown in equation 87. We then arrive at a solution shown in equation 88 for the minimum speed the rocket should be launched and it is about 7,000 meters per second. For letter B, we find the minimum speed that would allow the rocket to escape from the Earth completely. So, at the surface we still have equation 79 and 80. As the rocket is launched to escape Earth we set the distance to infinity. So the energies at infinity would be 0 as shown in equation 90 and 91. Equating the initial and final energies we have equation 84. Where it is further simplified from equation 92 and arrives at an expression in equation 93. After substituting the known values we have the speed of 11,000 as shown in equation 94. This is the minimum speed that would allow the rocket to escape from the Earth completely and it is also called the escape velocity. Here we see that it is independent of the mass of the rocket but only depends on the mass of Earth and its radius. So if you know the planet's mass and its radius, then you can calculate the initial speed you need in order to escape its gravitational effects. Of course you have to include the rotational speed of the planet and its air resistance.